roughly what it is?
Yeah.
So hi, I'm Andrea. I'm a postdoc with Umesh. The title really is more of a placeholder for me to describe my research interests a bit more broadly. In particular, to those of you who are not already working in quantum computing, I think there are not so many here, but hopefully some maybe on Zoom. So primarily, I'm interested in how we can leverage quantum information for cryptography. And as I'm sure you will have heard by now, quantum computers are expected, one day, at least in theory, to be able to break the cryptography that we use today. And while this is bad news for cryptography, the main message that I want to get across in this talk is that actually quantum information more than compensates for this. In fact, it turns out that we can leverage quantum information to realize cryptographic tasks that are in some cases impossible classically, and in other cases realize them from weaker assumptions than is known classically. So what is it that makes quantum information so special for cryptography? Well, at the heart of it is one simple theorem, which is called the no-cloning theorem. It's a consequence of the uncertainty principle, and it says that sort of a quantum state cannot be generically copied. What I mean by this is, classically given a string of bits, you can always make 2 copies of it. And this is essentially because you can always read a string without disturbing it. However, in the quantum world, there does not exist a universal copying procedure that takes as input an arbitrary unknown quantum state and produces 2 copies of it. And so, this is on the one hand bad news because it says, fundamentally, it is hard to store quantum information. But on the positive side, in a cryptographic setting, this means that you're significantly restricting the possible strategies that an attacker can perform. And so I guess the plan is to show you a little bit how this principle can help us. And before I do this, I think at least a few of you work in a very different field than quantum computing. So I just wanted to have one slide to give some essential information so that the rest makes a bit more sense. I guess this is at the cost of just saying what a qubit is to those of you who already work in quantum. So, as you have heard, a qubit is the quantum analog of a bit. It can be in a superposition of 0 and 1. Here, alpha and beta are complex numbers. And really, you should think of this as a 2-dimensional vector where the standard basis vectors are 0 and 1. So you can think of 0 as pointing upwards and 1 as pointing to the right. And any linear combination of the 2 is a valid qubit state. So for example, we could have 1 over square root of 2, 0 plus 1 over square root of 2, 1. This is sort of the vector pointing to the 45-degree angle. We could have the same state with a minus sign. This would correspond to minus 45-degree. And one really important thing is that really the only way to extract classical information from a quantum state is via a measurement. So you're allowed to ask the question, is the qubit state 0 or 1? And you will get an answer if you do so, a 0 or 1, depending on the probabilities will depend on the coefficients alpha and beta. And now the crucial difference for quantum information is that upon measurement, the state will collapse to the outcome that you observe. So you no longer have the state that you started with. And this is very important. And of course, you can ask the same question, is it 0, 1 with respect to any other basis? There's nothing special about the standard basis, and the post-measurement state will be one of the 2 orthogonal basis vectors. And so let's see how we can leverage all of this. So let's consider the task of key distribution. So in key distribution, we have 2 parties, Alice and Bob. They have a simple goal, which is to agree on a uniformly random secret key. This is a secret in the sense that it's known only to the two of them. And they would like to do this by communicating over a public communication channel. This is public in the sense that any malicious eavesdropper, Eve, can read everything that passes through the channel, intercept any message. So if you stop and think about this for a moment, you'll find that it's very difficult to come up with a key distribution protocol if Eve can intercept everything. In fact, it turns out that it's impossible, classically, to realize a key distribution with unconditional security. So what I mean here by unconditional security is that the security should be information theoretic. So it should hold even against the computationally unbounded eavesdropper. And this impossibility is quite easy to see. Any bit that Alice sends to Bob and vice versa can be intercepted by Eve, like so. And so eventually, at the end of any protocol, Eve and Bob will have seen exactly the same transcript. So if Bob was supposed to learn a key, then so information theoretically, so can Eve. Now, things are different in the quantum setting. Alice is not restricted to just sending bits. She can send qubits. For example, she could choose to send qubits in the standard basis or in the 45 minus 45 degree basis. But let's say that she chooses to send a bunch of qubits, and for each qubit she chooses uniformly at random between these 4 possible states. Now, of course, Eve can still intercept each qubit on the way from Alice to Bob, and she can try to learn some information about it. Okay, but the point is that Eve does not know the basis choice that Alice made, and so with at least half probability, Eve will be measuring in an incorrect basis. And this measurement, as a result, will disturb the state that eventually gets to Bob. And so the key is that, in a later step, Alice and Bob can reveal to each other their basis choices, and they can detect with high probability if Eve has tampered with a significant fraction of the communication. And if so, they will abort the protocol. So this is really the key idea here, and using this idea, one can realize key distribution quantumly with unconditional security. And this is something that we already knew in 1984 from a protocol of Bennett and Broussard. So there is this stark contrast between the quantum and the classical setting for key distribution. And the natural question is, can we go beyond key distribution? And unfortunately, the answer seems to be no. And this is because there is another primitive called bit commitment, which we know to be provably impossible to realize with unconditional security, even using quantum information. And unfortunately, bit commitment is a fairly basic primitive in cryptography. It is implied by many other more complex primitives. And so we seem to be a little bit out of luck here. And I think it's fair to say that for several years, over many years, quantum cryptography has focused more on the study of key distribution in various settings. And so what I want to highlight today is sort of a line of research that has emerged or gained traction a bit more recently, which I find most interesting, which is the following. So, in almost all of classical cryptography, or almost all of it, is based on computational hardness assumptions. What I mean by this is that the security of almost all cryptographic protocols is not unconditional, but it's based on the assumed hardness of some computational problem, like, for example, computing a discrete logarithm or factoring. And so why not try to combine quantum information with computational hardness in the hope of getting interesting cryptographic primitives, not with unconditional security, but at least from weaker assumptions than is possible classically. So let me just state briefly one example of this from a recent work. So the primitive is multiparty computation, which is more powerful than key distribution. It allows actually mutually distrustful parties to compute an arbitrary function of their joint inputs securely. So this is very powerful. Now, classically, we know how to build this based on various computational assumptions about specific problems. But crucially, we do not know how to build this from one-way functions. So just to remind you, a one-way function is a function that is easy to compute, but it's hard to invert on average. And the existence of one-way functions is pretty much the minimal assumption that we know to be useful for anything in cryptography. So ideally, we would like to reduce all of our primitives to one-way functions, but this does not seem to be the case for multi-party computation. In fact, there is a black box sort of impossibility here. However, it turns out that maybe surprisingly that in the quantum world, we can actually reduce multi-party computation all the way to the existence of one-way functions, and this is due to two recent concurrent results. So I guess I have one last comment, which is, in this case, multi-party computation is something that we already knew how to build, just classically, just from stronger assumptions. So this is I would say more of a qualitative result. However, there are very interesting examples where the combination of computational hardness and quantum information can really lead to new primitives that are even out of reach of what is possible classically. I think Chipeng later will talk about some of this. So thank you.
So any questions while Yassine is setting up?
So you said that one-way functions imply quantum multi-party communication. Is that like one-way functions that are secure to quantum inverters, or?
Yeah.
Okay.
Yeah, that is the case. Yeah.
Is there one more question?